All right, so good evening once again, ladies and gentlemen. So like I've already stated, in today's class we are going to look at carbohydrate, which is a continuation of our previous lecture class in carbohydrates. So this is the second class on carbohydrates. The next class I will be explaining on the same topic, but basically I'll be talking about polysaccharide. So can just someone kindly confirm with me if you guys are able to get me or not? Can someone just kindly confirm with me so that I'll be able to know if we are moving at the same pace or not? Are you able to get me?
Yes, sir. Yes, sir.
Okay, all right, that's good. So like we stated last time on classification of carbohydrates, we simply talked about carbohydrate being classified into three to four groups. Some books they say four groups, and other books they'll say 3 groups. So but basically when you talk of classification of carbohydrates, we normally classify them into 4 basic groups. For those who attended the first class, can someone please mention all the 4 groups of carbohydrates? Can someone explain the 4 groups of carbohydrates?
All right. We have monosaccharide,
Okay.
disaccharides, oligosaccharides, and polysaccharides.
Correct. So we have basically 4 groups of carbohydrates. We have monosaccharides, which are the monomers, and we have the disaccharide, which are made up of 2 monosaccharides. Then we have oligosaccharide, and lastly we have polysaccharides. So in today's class I'll start with isomerization. I'll start with isomerization of the monosaccharide, the isomerization of monosaccharide, and then we are going to proceed and talk about disaccharide. So that's where we are going to end. So when you talk of isomers, isomers can be classified into different types of isomers. So we have different types of isomers depending on the characteristics of that specific molecule or compound. The first type of isomer which we can talk about is stereoisomer. So when you talk of stereoisomers, these are just compounds having the same structural formula but are different in terms of configuration. So when you talk of stereoisomers, they have the same structural formula. Okay, they appear to have the same structural formula, but the difference comes in because of them having a difference in terms of configuration. So when you talk of stereoisomers, these isomers have a certain type or a special type of carbon which is known as the chiral carbon. I'm going to go in detail and I'm going to talk about what a chiral carbon is and also what happens to this configuration. So when you talk of this configuration is specifically due to the orientation of the hydrogen and the hydroxide. So you need to understand that the reason why we are having these isomers is just because of the configuration of the H and the OH group. So the H group is just the hydrogen group, and the OH group, it is just the hydroxyl group. So how these hydroxyl and the hydrogen group are oriented when you talk about the stereoisomers, these are the ones that will lead to us having the what? The configuration, the difference in terms of configuration. Now, when you talk of these hydrogen and OH group, so the hydrogen and OH group, like I have stated, they will help us to classify these isomers. They can be stereoisomers and some can be what? They can be structural isomers. So depending on what we are going to focus on. Now, when you talk of stereoisomers are due to the presence of what we are calling an asymmetric carbon. Okay, an asymmetric carbon is also known as a chiral carbon. An asymmetric carbon is also known as a chiral carbon, and this asymmetric carbon, it is just a carbon which is surrounded by 4 different groups. Remember, a chiral carbon or asymmetric carbon is a carbon which is attached to 4 different groups. 4 different groups. Okay, so the other name of an asymmetric carbon is also known as what? A chiral carbon. So when you define a chiral carbon, you can just use the same definition of an asymmetric carbon. So an asymmetric carbon is just a carbon which is attached to 4 different what? 4 different groups. We'll look at that later. So a very special molecule or monomer which we can try to use when we are trying to explain the asymmetric carbon or a chiral carbon is just using the what? Glycerohydride. So when you talk of a glycerohydride, this is simply a triose. This is a triose. Okay, so remember, the monosaccharides are being classified into different groups depending on the number of carbons. Remember that the monosaccharides are classified into different groups depending on the number of carbons. But here we are not picking everything. Instead, we are just selective and we are talking about what? A glycerohydride. We know that these type of isomers can also exist in glucose, they can exist in galactose, they can exist in fructose, they can exist in any monomer which is having a chiral carbon. And a chiral carbon is a carbon that has been attached to by 4 different groups, and due to the orientation of the hydrogen and hydroxyl group, this chiral carbon, which is also known as the asymmetric carbon, can lead to a special type of isomerization which is known as stereoisomers. Now, an asymmetric carbon is also known as a chiral carbon. I have already explained what a chiral carbon is. Like we have stated, a chiral carbon is made up of 4 different groups. Let's quickly move on. Now, the number of possible stereoisomers depends on the number of asymmetric carbons. The number of stereoisomers depends on the number of what? Of asymmetric or chiral carbon that are in that particular molecule. So the formula that can help you to know the number of stereoisomer a certain molecule has is just 2 to the power n, where n is the number of chiral carbons. Now let me quickly look at that particular diagram. So if you observe very well, I've written D and L form of glycerolide. So stereoisomers, they lead to the formation of two types of isomers. One is the D isomer, okay, and two is the L isomer. We are going to go in detail and look at what happens, specifically what happens to this molecule for it to be called a D isomer or L isomer. So initially we just talked about the examples of trioses, which is glycerolide and the other guy. Now I've just picked glycerolide alone as it is. It can exist in two types. Why? Because of the presence of what? Of the chiral carbon. So this carbon here, if you observe, what is down here is different from what is on top, and what is on the left is different from what is on the right. As a result, this carbon here is known as the chiral carbon or the chiral center. This carbon here is known as the asymmetric carbon or the chiral carbon. The reason why it is called the asymmetric carbon, it's because it is having four different groups. One there, two there, three there, four there, four different groups attached to it. Any changes, let's say if this side there was OH, then it's not a chiral carbon. Now, with that in mind, this chiral carbon will lead to the formation of two types of isomers, a D and L isomer. In this case, this is known as D-glycerolide, and this other one is known as L-glycerolide. We are going to look at why is it called D and why is it called L in the later part. So for this part, do we have anyone with a question? Anyone with a question to kindly ask? Feel free to ask. Do we have any question? Okay, it's like no one has a question. Let's move on. So this the orientation of the OH group. If you look at the OH group and the H group, the D-glycerolide, the OH group is on the what? The OH group is on your right hand side. When you talk of the D-glycerolide, the OH group is on the right hand side. When you talk of the L-glycerolide, the OH group is on your left hand side. Now let's quickly move on and look at that. Now the configuration of the H and OH at the second carbon of the glycerolide will form two mirror images. It will form two mirror images. If you look at this one, it's more like this molecule, the D-glycerolide, it's more like it's looking at the mirror. Remember, let's say this is a mirror. Okay, if this is the mirror, this guy is looking at it. Even you yourself, when you look at yourself in the mirror, you need to understand that your face will be looking at you. Your face will be looking at you, and you're going to be looking at the image which is in the mirror. Same applies with the stereoisomers. So this glycerolide, it's looking at itself in the mirror. Remember, the OH need to be on your right hand side for D-glycerolide, and your OH need to be on your left hand side when you are talking about the L-glycerolide. Now, the the stereoisomers, they lead to the formation of D isomer and L isomers. So mostly when you talk about this, you need to understand that all the monosaccharides, they are just derived from glycerohydride. All the monosaccharides are derived from the glycerohydride. There is just an addition of the carbon atom. Then the same stereoisomer, the same arrangement, is also known as the absolute configuration. Now let's talk about this same chirocarbon. Let's specifically talk about this chirocarbon. So the chirocarbon makes a molecule to be optical active. A chirocarbon of any molecule, in this case we are talking about carbohydrate, will lead to that molecule to be optical active. The word optical, it simply means that there is light involved. So when a molecule is optical active, in this case, in case of a chirocarbon, one thing you need to understand that an optical activity is due to the presence of a chirocarbon, which is known as the asymmetric carbon. So a molecule can only be optical active when there is a chirocarbon in it. Now this molecule, when it is being exposed to light, when a molecule which is optical active or a molecule which is having an asymmetric carbon, when it is exposed to light and this light has to be polarized, this molecule can either rotate to the right or to the left. I'm repeating that. A molecule which has a chirocarbon, when it is exposed to polarized light, it will either rotate to the left or to the right. Now, when a molecule rotates to the right, it is known as dextrorotatory. When a molecule rotates to the right, it is known as dextrorotatory. Dextrorotatory. So dextrorotatory, it's the name which is given to a molecule which is rotated to the right when it is exposed to what we are calling a polarized light. And this polarized light, it is a light which is going to act on an asymmetric molecule or a molecule that is having a chirocarbon, and this molecule will rotate to the right. Now, when a molecule rotates to the left, it is known as levo rotatory. So the levo rotatory, it is the name which is given to the isomer which rotates to the left. That's why you are having D-glycerohydride, meaning it's rotated to the right, and L-glycerohydride because it's rotated to the left. And the reason is that this glycerohydride has a chirocarbon in it. Now, we have what we are calling a racemic mixture. So when you talk of a racemic mixture, this is whereby there is no single rotation. There is no single rotation. But for this part, it will normally be explained more in chemistry. So I think at this particular point, I can allow people to ask questions and I'll be able to respond. Do we have anyone with a question? Please feel free to ask. Any question? Please just unmute yourself. Yes, what's your question?
Yes, sir, I have a question on the third point on optical activity. Can you kindly repeat that?
Okay, optical activity, it is the situation where a molecule which is having an asymmetric carbon or a carbon with a chiral carbon undergoes a rotation, and this rotation can either be to the left or to the right. When a molecule rotates to the left, it is known as the levo rotatory, and it's normally negative. So levo rotatory, it is the name which will be in front of that molecule. For example, L-glycerolhalide. It simply means that that molecule rotated to the left. When you talk of dextrorotatory, this is normally positive, and this molecule has rotated toward the right. That's why you're having D-glycerolhalide, and this is because of the chiral carbon present. Is that okay? Is that okay? The guy who asked?
Yes, sir. It's okay now.
Okay. Any other person with a question? Okay, we move. Now, look guys, I said there are different types of isomers. Now, we have just mentioned stereoisomers, but we also have another set of isomers which are known as epimers. A very good example of an epimer of glucose is mannose. Another example of an epimer of glucose is galactose. Now, these epimers, these are just isomers which are only having a difference at a single carbon. At a single carbon. Not two, not three, not because of the rotation, but because of what? The orientation of hydrogen and oxygen at a single carbon. Actually, epimers can also be said to be structural isomers. Epimers can also be said to be structural isomers because these guys have the same molecular formula. The only difference is the orientation at only a single carbon. Now, for example, glucose and mannose are example of an epimer pair, and these they only differ at carbon number 2. I'm repeating this because it is an exam question. Mannose is an epimer of glucose, and they only differ at carbon number 2. Take note of the number of the carbon. Carbon number 2. That's where you can see the difference between glucose and mannose. Another epimer is galactose, and galactose is an epimer of glucose, and they only differ at carbon number 4. So these are the two good examples of epimers of glucose which you can be asked in an exam, test, or a quiz. They only differ at one single carbon. The first one is mannose. The difference between mannose and glucose, it has carbon number 2. Then when you talk of galactose, the difference between galactose and glucose is carbon number 4. That's the diagram, which is just illustrating what I have explained. So the one at the center is glucose. The one at the center is glucose. Remember that glucose is also having stereoisomers. Yes, it is having epimers, but it is also having what? Stereoisomers, because we have L-glucose and D-glucose. We have L-glucose and D-glucose. I'm going to make a revision class on orientation and changes of glucose in different forms. That will be outside the class. Now, if you look at the difference between glucose and mannose, you need to understand that they are only differing at carbon number 2. So there and there. That's where there is a difference between glucose and galactose, glucose and mannose. Then when you talk of glucose and galactose, the only difference is only carbon number 4, which is this one and that one. So this is where you only expect the difference between glucose and galactose on carbon number 4. And this is just because of the orientation. So glucose, the OH is on the what? On the left. But when you talk of galactose, the glucose, the OH is on right, just like we know about D-glucose, but for galactose is on the left. Now, before we go and do the saccharides, do we have any questions? Okay, I can see Florence has a question. What's your question, Florence?
So can you repeat on the examples of impediments where you're explaining about glucose and mannose? Not this page, but the previous one.
This one?
Yes.
Glucose and mannose are epimers because they are different at carbon number 2. Galactose and glucose are epimers because they only differ at carbon number 4. Mannose and galactose are not epimers, but they are structural isomers. You get that now?
Yes, thank you very much.
You're welcome. So let's quickly look at okay, I can see a hand. Yes, what's your question? The person who has raised their hand. Taonga, what's your question?
On the previous page, sir.
Yes.
Not this one. Why is it that mannose and galactose are not epimers?
Okay. Mannose and galactose are not epimers, but they are structural isomers. Why? Look, there is no difference between the orientation between mannose and galactose is okay. What can I say? You only compare at a single carbon. So like this one is the main nigger, the glucose is the main guy, and from glucose that's where you can get galactose, and from glucose that's where you can get mannose. That's why we normally refer these two guys to glucose. But if you go further studies, I'm sure more can be reviewed, but basically for your information at this particular level, you normally concentrate much on glucose, and you compare glucose to galactose and glucose to mannose. The reason why is that most of the disaccharides will start talking about, and polysaccharides, they will involve these guys. Is that okay, Taonga?
Yes.
Okay, we move. So let's talk about disaccharides. So here I'll be a bit fast. So when you talk of disaccharides, so when two monosaccharides are combined together, there is an elimination of water. So when water is eliminated, that simply means that this reaction is a condensation reaction. So during the formation of disaccharide, there is the removal of of water. So the removal of water makes this reaction to be a condensation reaction. Then when two monosaccharides react together, they do form what we are calling a disaccharide. Now, this bond which exists between monosaccharide is known as a glycosidic bond. A bond, this one, a bond between two monosaccharides is a glycosidic bond, and this bond is just a covalent bond. This bond is just a covalent bond, and this bond is the bond which exists when two monosaccharides react together. Now, examples of disaccharides, we have sucrose, maltose, and lactose. Examples of disaccharides, we have maltose, sucrose, and the lactose. I'll start with the sucrose. The reason why I'm starting with sucrose is because this is a special disaccharide. 1. This is the basic structure of sucrose. This is the structure of sucrose. You need to be able to draw for the sake of quiz. So you need to be able to draw the structure of sucrose. So during a quiz, mostly it is not multiple choice, and they might ask you to draw. So this is the structure of sucrose. Now, sucrose is also known as saccharose. Sucrose is also known as saccharose, and this is just the normal table sugar. The sugar you put in your tea, the sugar you use, the sugar which is in your houses, is the one which we are calling sucrose. Now, this sucrose is not a reducing sugar. This is the special feature of sucrose. It is not a reducing sugar. Then, the reason why it is not a reducing sugar is because of the bond linkage which takes place during the formation. You need to understand that sucrose is made up of glucose and fructose. The monomers in sucrose, are glucose and and fructose. Now, the bond is between the first carbon and the second carbon of galactose. The bond between the glucose and fructose is between the first carbon of glucose. So this is the first carbon of glucose here, and the second carbon of of galactose. The first carbon of glucose and the second carbon of galactose. So that bond between these two guys is the one which makes this sucrose to be to be a non-reducing sugar. So when sucrose is hydrolyzed, the resulting product have no reducing properties. Okay, now this is how the formation of sucrose is. So if you look at the formation of sucrose, you have glucose here. This is glucose, and you also have fructose there. So glucose, this guy here will react with an H which is there. Will react with an H which is there. There is an H there. Okay, so when you see nothing has been indicated, then there is an H everywhere here. There is an H in a ring structure. If you can't see anything, then there is an H there. There is an H there. There is also an H. So during the formation of sucrose, during the formation of sucrose, the carbon number 1 of glucose will react with the carbon number 2 of fructose. So this one here will react with that one. So what will happen is the OH will react with the H. Okay, the OH will react with the H to produce what we are calling water. And then a bond will exist between these two guys, and that bond is the one which has been formed here. So the bond here which has been presented in red, it is what we are calling the glycosidic bond. So it is normally the 1,2 glycosidic bond. 1,2 glycosidic bond. A 1 is from the fact that it is the first carbon of glucose, and the 2 is the second carbon of fructose. Yes, I've seen an hand. Okay, sure, the person. Okay, let's move on. So this reaction is a condensation reaction because water has been produced. This reaction is a condensation reaction because water has been produced. And this bond here, it is just the 1,2 glycosidic bond. Okay, we move. Now, let's quickly look at lactose. Lactose is a type of disaccharide which is found in milk. The same milk you take every morning or every day, it is due to it contains what we are calling lactose. Now lactose is a reducing sugar. Lactose is a reducing sugar, and that's how it looks like. And in lactose there is that glycosidic bond. So the bond you are able to see there, it is what? It is a glycosidic bond. So this is a glycosidic bond, a bond that is existing there. Now, what makes up lactose? So lactose is made up of galactose and glucose. Mostly it is beta beta D galactose and alpha D glucose. So the bond exists between the first carbon of galactose and the fourth carbon of glucose. The bond exists between the first carbon of galactose and the fourth carbon of glucose. In sucrose, it was the first carbon of glucose and the second carbon of fructose. So these are the guys which normally takes place. Remember, the body has a lot of D-glucose. Take note of that. The body has a lot of D-glucose. So with that information, this guy, they are going to react, the hydrogen there and the OH there, they are going to react to produce what? To produce water. To produce water. Water will be also be released, H2O. Now, this bond which is going to exist during the formation of lactose, and this formation is between galactose and the glucose. This reaction is a condensation reaction. But in a case when water is added, meaning when we want to take back lactose to its subunit, then that's known as the hydrolysis. So hydrolysis taking back this side, okay? But the reaction we are much focusing on, it's taking these two to that, which is a condensation reaction, and you can see water has been released. Now, a bond exists between these two molecules, which is particular this bond here, which is particular the bond which is existing here. This bond is the 1,4 glycosidic bond. 1,4 glycosidic bond. Take note of the 1, what? 1, what? Those are important because they'll ask you what type of bond is in what? In lactose. So you should be able to say that it is a 1,4 glycosidic bond. Okay. Do you have any question before I move on? What's your question, Florence?
So I wanted to ask, why is it that it's a 1,4 glycosidic bond?
Because the carbon which is taking part is the first carbon of galactose and the fourth carbon of glucose. Fourth carbon of glucose. You have 1 there, 2 there, 3. This is the fourth one. Then this one, this is the first one. Is that okay? Is that okay?
Yeah, it is okay, but I've seen that in the one. Now, how are you counting them?
You start from this one. You start from, you have oxygen there, then you are going to start with this one. You say 1, then you go 2, then you go 3, then you go 4, then you go 5, and then lastly you go 6, making it 6 carbon. Then this one will go 1, 2, 3, 4, 5, 6. So you start from that oxygen there, don't count it in the ring structure. Then you start from that one. We'll talk more about the ring structures on one of the topics where I will talk about the furanose and also the puranose. So yeah, I'll talk about that. Okay, any question? Any question? Yes, Charles, what's your question?
Yes, when you were talking about the sucrose, you said that is the most special. What makes it to be special?
It is what? It is not a reducing sugar. It is not a reducing sugar, but this one is a reducing sugar. That's the special case of sucrose. It is not a reducing sugar. Is that okay?
Yes, I'm clear now.
Okay. Let's quickly look at the last one, which is maltose. So maltose, it's normally made up of alpha D glucose. Alpha D glucose. Alpha D glucose. 2 alpha D glucose. And this one is a reducing sugar, and that's how it looks like. That's how it looks like. So when you talk of the formation of maltose, that's what happens. So normally the same thing I explained about lactose, the same thing I explained, but in this case it is just that this one is alpha D glucose and that one is alpha D glucose. By the way, remember the galactose which was in lactose, it is beta D galactose, and alpha D glucose. So that's how the maltose is formed, and the bond here, this bond here, it is just the 1,4 glycosidic bond, of which you need to understand that this is a condensation reaction. I think that's all for today. I don't know if there is any question, but if you have any question, you can ask now, or you can simply inbox me on those